Hello everyone. So today we will be talking about the resonance, specifically the parallel resonance. So before delving into that, let us see what is resonance. So we have here the definition of the resonance in an electrical way, but first we will see some figures to illustrate what is resonance in the real life situation. So resonance can be of this situation when you see this glass that is broken, shattered in two pieces. When a singer sings, when this when the frequency of the singer equate to the natural frequency of this glass, the property of this glass, it is called resonance. So nag-equate ang ilahang frequency from the end of the audio or the singer to the property, the frequency, the natural frequency of the glass. Then it shatters because there is na-strike ka ng signal or intensity nga ni nag-vibrate siya, naka-cause of vibration, then it shatter. It may cause shatter, but unsahay listener siya i-attain nga kana nga resonance. So na tendency nga dili jud siya ma-shatter, but naa siya tendency nga ma-disturb niya ang katong natural frequency, and then it cause some vibration to that object. And also we have here a swing. So as you can see, sa ato ganing mag-swing ta, we are trying to push somebody or someone or something in an object siguro. Kung mabantay nato, ga-push ta in a certain way nga hinay ra siya, but matingata nga taas ang naabta niya. It swings farther than we are expecting. That is because katong pag-push nato, ang frequency nga sa pag-push nato equates to the natural frequency of that swing. So mo na siyang nahitabo. And we have here the third picture here, a bridge that is broken. Naguba ang bridge. It was destroyed because probably in an earthquake or a vibration from the vehicles that is passing through that bridge naka-cause og certain vibration nga ni-equate sa natural frequency sa bridge, then it broken down. So as you can see, this resonant frequency can be desired or not desired depending on the application nga atong gamiton. So with that fact, pwede nato siya magamit in a certain way nga to be on our advantage as an electrical engineer. So let us define first what is a resonance in an electrical way. So resonance is a condition that exists when the inductive reactance and the capacitive reactance are of equal magnitude, causing electrical energy to oscillate between the magnetic field of the inductor and the electric field of the capacitor. In that way, it implies nga kini ma-purely resistive lang jud ang atong impedance or admittance, kay ma-equate man ang inductive reactance and capacitive reactance. So let us illustrate that into a schematic and some equations. So we have here a circuit that is parallel. We have an input source of a current. So we can compute the admittance that is in this circuit. So we have here the equation. So in order for this to satisfy the resonance, we must equate the capacitive reactance and the inductive reactance of this equation. So with that, omega sub c minus omega sub l is equal to 0. And with that, we can compute for the natural resonant frequency of that circuit with this equation, 1 over square root over LC. Og nakalimtan nako ang LC dire. So and the FO because omega sub O is equal to 2 pi f, right? And putting the 2 pi in the denominator, so we have the resonance frequency equal to 1 over 2 pi square root LC. So that's it. And also, we can take the advantage of these admittance forms to find the roots of the equation and find the poles and zeros of that certain equation, certain circuit, so that kung mag-design man gud ta, labi na sa katong sa mga AC nga mga application, it is important for us to determine the poles and zeros to adjust, labi na kung mag-define ta o ganing mag-match ta og mga impedances, and we want to satisfy some certain kanang conditions to match some circuits. So with that, mo na siya ang equation, and we can represent it in an S domain to compute the transfer function, and with that we simplify it and we arrive with this equation, substituting that alpha is equal to 1 over 2 pi RC. This is a damping coefficient, and omega sub D is the natural frequency, which is equal to the resonance frequency squared minus the damping factor squared. So this damping factor would determine the damping characteristic of our circuit, which is same with your previous nga mga lessons sa EE 101. So I hope you have remembered it. So if not, kindly revisit your EE 101 bang electrical circuits nga klase. Okay, that's it, and we will proceed to another topic. Now let us see the resonance and the voltage response of the parallel circuit. So as you can see here, we have here some kind of a bell curve. So in the middle is the frequency at resonance. So kung makita ninyo, ang magnitude nato is which is in here is the voltage, not in power, but as you can see, our voltage output here is nakadepend lang sa R, no other values of R. And as you can see here, we have here the cutoff frequency, which is calculated at 0.707 times the magnitude of the R, in which probably we will talk about deeply in the later sections. So actually this 0.707 magnitude is the minus or plus 3 dB of that magnitude, which is referred as the cutoff power kung maghisgot ta og power. But for now, let's just see to it na mo na siya ang mga values nga maingon ta og the cutoff frequency. And this cutoff frequency, which is referred to as, probably will be talking it here as the upper bound and lower bound as the to be calculated as to be the bandwidth of that signal. And we also have here the quality factor of the RLC circuit that can be calculated as the 2 pi times the maximum energy stored over the total energy loss per period. As we all know that the inductor and the capacitor are the storage passive devices that can store energy. So in that matter, we can calculate the energies stored in the energy that is stored in the capacitor and inductor. And for the energy loss, we can calculate that in the power consumed by the passive resistance, passive device, which is the resistor. So let us define that first. So with that definition, we can say that the quality factor is equal to 2 pi times the energy stored in the inductor plus the energy stored in the capacitor with respect to time, and over the power lost in the resistor with respect to time, of course. So, and for that, we can define for the forcing function that is applied in the parallel circuit before, katong parallel ang current source, let that forcing function equal to Im cosine omega sub t. And next is we have the with that forcing function, we can have the voltage response on that for the for that circuit to be kay mo na sa resonance, diba? Kay resonance maximum siya. So resistor lang mabilin. So we have our Im cosine omega sub t, and we calculate for the energy stored in the capacitor to be 1/2 CV squared. So substituting that, so we have 1/2 times C times the voltage Rim cosine omega t squared. So we have this value. And for the inductor, we have the energy stored in that, so we have 1/2 Li squared. So we have 1/2 times L times the inductor computed in that, the inductor current that is computed in that is 1/2 times the integral of V dt squared. So in here, as we calculate, kasing ka-wonder mo, so we have 1/2 times L, diba? Squared man eh. And we expect that 1/2 times L is 1/2 L squared. So, ma-cancel ni siya, kaya ma-L squared naman ni. So, ang mabili na lang is L. Then, substitute the integral of V, integral ani. So, which is, kana times squared. So we have this value for the energy stored in the inductor, and then we have, okay, so simplifying that, so we have Im squared R squared C over 2, and then so this in here is the total power that is stored in the energy storage in the inductor and capacitor. So total na ni siya. So we sum up the energy stored in the capacitor plus the energy stored in the inductor, which is equivalent to this. And so we have the energy stored. Now we can calculate the energy lost per period. So the energy lost is the power that is consumed by the resistor, and to take that into the average value of that period, so we can calculate, so we can multiply this power resistor by the period. So we have PR times T, or the reciprocal of period is just equal to 1 over the frequency. So we have just substitute the value of the period, which is 1 over FO times this. So we have this total energy loss per period. And so we already have the maximum energy stored and the total energy lost per period. Now we can calculate the quality factor to be, which is this. And then simplifying it further, we can have 2 pi times the frequency RC, or equivalent to resonant frequency times RC. And then simplifying it further, So, ano siya? Then, we know that omega sub O, the value of omega sub O is, okay, and we know that omega sub O is equal to 1 over square root of LC. So, since over square root of LC, what we have left is times a quality factor is equal to R square root of C over L. Since kini siya is, kung i-simplify lang nato further, C is equal to 1. LC 1 over square root of LC times C, diba? I-exclude na tong R dito. So, C, ang exponent niya 1, 1 minus negative 1 half. So, we have square root of C na lang. Then, mabilin ang L. So, muna siyang square root of C over L. Or, we can express that into R over the absolute value of the magnitude of the reactive capacitance, or equal to R over the reactive capacitance of the inductance, since these two are just equivalent. Next is the damping factors. For future reference, it may be helpful to note one additional relationship involving the resonant frequency and the quality factor. So the quadratic factor appearing in the numerator in here can be written in the terms of alpha and the resonant frequency. So we have S squared plus 2 alpha S plus omega sub O squared, which is the resonant frequency. And in the field of system theory or automatic control theory, it is traditional to write this factor in a slightly different form that utilizes the dimension parameter zeta. Here, this is zeta, called the damping factor. So this is called the damping factor. Hindi ko kasulat. Damping factor ni siya, which is equivalent and can be written equal to alpha over omega sub O, or equivalent to 1 over 2 U sub O, which is the quality factor and the resonant frequency. So we can see the relationship between the quality factor and the resonant frequency in terms of zeta. So for the next video, we will show you some example considering a parallel RLC and determine some values in there. So see you then.